Hey everyone, welcome to the unit on electricity and electrochemistry. So this is chapter 20 in your textbook. Anyway, it says here that we're just going to start with kind of like a basic introduction, and a lot of the content in chapter 20 in your textbook is no longer relevant to the newer AP exam. So we'll be skipping a bit of content. You'll notice that as we go through. But let's go ahead and get started here. It says electrochemistry. So certain chemical reactions produce electricity. And also, electricity can actually force certain chemical reactions that normally don't occur spontaneously to work. Like we can push non-spontaneous reactions to go. And so we're going to take a look at both of these cases here. Let's check it out. First, a bit of a review. What is electricity? Well, electricity is the movement of electrons from one place to another, typically through a wire. And another bit of review is the difference between oxidation and reduction. So oxidation is the loss of electrons, and reduction would be the gain of electrons. And you can't have one without the other. And I think I taught you guys an old way to remember this is oil rig. Oxidation is loss, and reduction is gain. So oil rig kind of helps students remember that one. So because oxidation always occurs with reduction, you know, these guys happen in pairs, typically what we want to see in a chemical reaction is we want to see one metal, we'll call it like metal A, losing the electron, and then a different metal, we'll call that metal B, being able to pick up that electron. So you can't have one without the other. Here's a great example. Zinc has a positive 2 charge. And so when zinc, the metal, the solid metal, becomes zinc, the ion, he will have a tendency to lose those 2 electrons. So he's going to pop 2 electrons off. And then if you were to take something like copper, the ion, right, you see how this ion over here has a positive 2 charge. This copper ion is highly attracted to electrons. And so if we can somehow move the electrons from zinc to copper, the ion, we can actually have an oxidation-reduction pair, a very nice little pair. And this reaction here we would say is spontaneous. It happens by itself. We don't have to push it. This reaction right here goes without any outside influence. So one of the things I want you to try to remember, because we'll talk about this a little bit later on, is that when zinc, the metal, loses 2 of his electrons, he will become zinc, the ion, positive 2 charge. And then when copper, the ion, is capable of gaining 2 electrons, he will turn into copper, the metal. So why does this reaction occur spontaneously? That should be your question in your head. Well, zinc, turns out, it has a lower attraction for electrons. It doesn't necessarily want to gain electrons, right? I mean, all metals are losers. They like to lose electrons, right? But what's interesting is that between the two of them, zinc versus copper, copper has a greater ability to grab onto electrons. So this level of attraction for electrons is sometimes called the reduction potential. Think back to the difference between oxidation and reduction. Reduction is gaining electrons. So, you know, oil rig. So rig, reduction is gaining electrons. So it turns out that copper actually does have a greater ability to attract electrons than zinc. So you're probably thinking, okay, well, we probably want to be able to predict which metal is going to be better at grabbing electrons and which metal is going to be better at releasing those electrons. And it turns out, hey, we do have that information. It's already been tabulated. Anyway, reduction potentials can be looked up, and the stronger the attraction, the stronger that the metal has for an attraction for electrons, the more positive the value will be. So these guys towards the top have a very large reduction potential, and these guys down at the bottom have a very low reduction potential. And the thing you have to remember is that all of these voltage potentials, they are measured under standard conditions. So what we like to see is if there's any gases involved, we want those gases to be at 1 atmosphere. All the solutions are going to be 1 molar, and the temperatures of these solutions and everything like that is going to be 25 degrees Celsius. All right, so those are called standard reduction cell potentials, or half cell potentials. All right, the next thing that we have to clarify is the difference between a galvanic cell and an electrolytic cell. So galvanic cells are sometimes called voltaic cells, and these are the type of reactions that occur spontaneously. You have one metal that just definitely wants to lose electrons, and the other metal that would like to gain those electrons for you. The electricity flows spontaneously from one metal to another. We don't have to push it. But in an electrolytic cell, this process is not necessarily spontaneous. So using the example from before, you have metal A that doesn't necessarily want to release any electrons. And then over here you have metal B that doesn't really want to gain electrons. But what we can do is we can actually force these two metals to give up electrons or absorb electrons. And the way that we do that is we connect these two metals, with some kind of wire. But then in between, what we like to do is we like to place a battery. So I'll place a battery right here that will make the electrons be pulled away from one of the metals and then force those electrons to be pushed into one of the other metals to receive that electron. So even if one metal doesn't necessarily want to lose electrons and the other one doesn't really want to gain those electrons, we can force it to work with the process of a battery or some other electrical source. So what we have in this picture is we have a galvanic cell on the left. This is the one that happens spontaneously. And we have an electrolytic cell on the right where we have had to plug in a power source. That's what you're seeing right here. So either a battery or some kind of power source is used to push those electrons and pull the electrons from the from one metal to another. So it's time to talk a little bit about some vocabulary. In both of these diagrams, you see the use of these words anode and cathode, and then you see this negative and positive sign. So it's time for a little vocab check. The anode is where we always have oxidation occurring. Oxidation occurs when the electrons are being produced. In other words, the metal is producing those electrons. It's typically going from, like in our previous example, that would be our zinc metal, right? The solid, turning into zinc the ion. You see, how does a zinc become positive? Well, he have a positive charge. He has to lose a couple of electrons to make that happen. So electrons are being produced at the anode. So in our previous example, this would have been the zinc side. And then the cathode, this is where reduction occurs, and reduction is where we have the electrons being absorbed, and is typically symbolized with a positive sign. So in our previous example, this would have been like our copper ion. See how it's got a positive 2 charge? If it absorbs a couple of electrons, it's going to become neutral copper, just the metal. And so what I think is so interesting about this is that technically your anode is turning from zinc the metal to zinc the ion. So you literally have chunks of metal, chunks of zinc falling off of the actual metal piece, this anode, and becoming zinc the ion in solution. So what's interesting is that this little electrode right here is actually losing mass because the metal literally falls off and goes into solution. And then the opposite is true for the other side. On the other side, you've got some copper ion floating around in solution, right? When the electrons pass over, from the zinc to the copper, and those electrons are being, pushed over to this side, those electrons are going to be attracted to the copper that's inside of the solution. And when that happens, the copper from the solution is literally going to come up and attach itself to this electrode, and this electrode will actually gain mass. So on one side you have the electrode losing mass, and on the other side you have the electrode gaining mass. That's what I think is so interesting. And the words anode and cathode can be sometimes very easily confused from students. They can't remember. So this is a clever little idea over here. Think about two different animals. We have an ox and a cat. So we have an ox and a red cat. And that'll kind of help you maybe remember that in the future. So what we're going to do now is we're going to separate and split apart the two metals into two separate containers. And the whole reason why we're doing that is because it allows us to stretch out the wire over a further distance. And it allows us to do more with the electricity in between. You know, if you have more space, we're allowed to do more things in the middle here. So when you split the two metals into two separate containers and you make those electrons travel a further distance, you're able to do more work with that electricity. And so it's definitely advantageous to have them separated. But you run into a bit of a problem. You see, the way a circuit technically works is you have to have a connection between the positive and the negative. You would never want the charge to be incapable of coming full circle. So if we have an electron traveling, as you know, the electron is going to travel from the zinc up here. So this zinc right here is going to have some electrons traveling up here, technically 2 electrons for every zinc, and we'll have a chunk of zinc fall off of the electrode and become part of the solution. Okay, and so these 2 electrons are going to travel down over here, and we're going to come over here, and these electrons are going to come down through this electrode, and it's going to find, these electrons are going to cluster themselves right here, and they're going to, these guys right here, they're going to find that copper ion in solution and bring it up over here and change it from copper ion in solution to copper metal, and it's going to coat that electrode. But when this happens, you have to understand that we're technically going to have a buildup on both of these sides. We're going to have a buildup of zinc over here. We're going to have a buildup of positive over here. And then if you look over here, because we're changing this copper ion, right, into copper metal, you're going to have an abundance over on the left side. You're going to have abundance of positive charge in the solution. And then because you're sucking up all of those positive copper ions, you're going to have a bit of a deficit of positive charges over here. So it's going to feel a little bit more negative. On the left, it's going to become more positive, and on the right, it's technically going to become a little bit more negative because you're sucking up all of those ions. And so what we like to do is, in order to complete a circuit, we want both of these cells, we just call these containers cells, we want both of these cells to remain electrically neutral. We don't want any buildup of charge going on. So sometimes what is necessary is the presence of something called a salt bridge. All right, and a salt bridge balances out charges. All right, and that's a good thing, because if we build up charges on either side of this cell, it's actually not going to be able to establish an equilibrium very well. So we want to keep that charge in check. So a common salt that they like to use is either potassium or sodium nitrate, because we definitely don't want to make any precipitates, right? So typically we like to throw an alkali metal with some kind of nitrate, because all nitrates are soluble, right? So for example, if I threw into the salt bridge some sodium ions, and then I also throw in some nitrate ions, let's think about where they would be most likely attracted. So over on the right side, this side, all of the positive ions were being sucked up, right? So why don't we replace some of those positive ions that were being sucked up? So you see how I've got some sodium? The sodium is going to rush down over here through this salt bridge. Is basically just a pathway for the ions to travel through. And so the sodium is going to rush to replace all of the copper that's being sucked up, all the copper positive ions. And then over on the left side, you see how we are producing a whole bunch of zinc, and zinc ions, they're positively charged. Well, over on the left side, we're going to take some of this nitrate, and you see how it's negative, and we're going to counteract that buildup of positive charge by pushing some of that nitrate down over in this side. All right, so that just kind of explains the general flow of ions and the general flow of electrons. So remember, which one's the cathode and which one's the anode? Do you remember? So over on the left, technically what we had is we had solid zinc turning into zinc the ion. And we were producing some electrons here, right? 2 electrons. So if you're making electrons, it means technically what this guy is doing is he's losing those electrons. He's getting rid of those electrons. He's pumping out electrons. So if he's losing electrons, this is where your oxidation is going on. All right, do you remember which one was the oxidation side? Think about an ox. So this is your anode. All right, this is your anode. And then over here, this is going to be where the reduction is going on. See the red? You should think cathode. There you go. All right, I hope that helped out a little bit. Okay, so next up, we're going to talk a little bit about how you measure something called cell voltage. The voltage the pull of electrons, basically, through that wire that goes through the top. So what you can sometimes see is some people, what they'll do is on this wire, they'll attach something called a voltmeter. Okay, and the voltmeter will basically tell you how many electrons are passing through the circuit and how fast they're moving through the circuit. So oxidation can only occur when reduction also occurs, right? They happen in pairs. So in our example, we had zinc the metal turning into zinc the ion, and electrons were being made, and that's oxidation. And then the reduction side, we had copper ion, absorbing those electrons and turning into copper the metal, and that was our reduction. When you combine these two, technically what they are is they're half reactions. When you combine those two half reactions, look at what's over on the reactant side. So if you could just kind of split the reaction and just look at both of these guys on the reactant side, on the left side of the arrow, technically what you have is you have zinc the metal and zinc the ion. And then you'll notice that I've got 2 electrons on right here. But technically you see how on the product side of the other guy right here, you also have 2 electrons. So these kind of get canceled out. And many of you guys remember from like previous units, anything that's similar on both sides of the 2 little halves get canceled out. So that's why over on the left, all you see is the zinc metal and the copper the ion. And then on the right side, we have zinc the ion and copper the metal. So the key thing about these voltage cells is that the number of electrons moving has to be perfectly balanced. So if one of the half reactions makes 2 electrons, the other one has to be able to absorb those 2 electrons. It has to balance itself. So now what we're going to do is we're going to look at some of the tabulated values that I showed you before. They're all tabulated, right? Let's see how you use them. So in our reaction, zinc solid is turning into zinc ion. When I look at the standard reduction value that was tabulated, I see that there is a negative 7.6 volts. But is this reaction technically a reduction process? Well, no, this is oxidation. Remember, we already talked about that. So just remember that all of the tabulated values are technically reduction values. So if you're going to flip the reaction, which I need to flip this, this is for reduction, this value is for reduction. I need to flip that value because I'm not doing reduction, I'm doing oxidation. So if you are flipping, if you're reversing the process, it's not technically what we need is oxidation, you got to just flip the sign. So in copper, you need to ask yourself, is this process that you are looking at, is this reduction? And yes it is, because technically you see this ion right here, the positive 2 is going away and there's no charge over on the right side. So that is definitely reduction. We're going from a positive 2 charge to 0 charge because it's a solid. So yeah, the reduction value that I looked up on the that I saw that was tabulated, it is 0.34 positive. All right, so what we're going to do is we're going to flip the sign of the negative 0.76 and combine it with the 0.34, and I get a total value of 1.10 volts, which is the standard reduction cell potential for that particular reaction. Okay, the total voltage that reaction can pull is 1.10 volts under standard conditions. All right, now I did want to talk about something that the book shows you, which I just thought, kind of makes sense. So it tells you that whenever you are calculating the electrical potential of a reaction, that you're going to want to take the standard reduction cell potential that they give you for the cathode, which cathode has reduction, remember red cat, and then it says to subtract the reduction cell potential for the anode, which is the oxidation process. But remember, all of the values that are tabulated are reduction values. So that explains why they put that negative sign in the middle. Basically what they're doing is they are flipping the sign like we had to do. They're flipping one of the signs because we want the overall E to be as positive as possible. Positive values are a good thing. Which brings us back to this whole idea of when can a electrochemical cell be spontaneous? How can we get that electricity to be formed? And this brings us also back to Gibbs free energy. So there's a relationship between the E standard and your Gibbs free energy. You remember, we've already talked about this, we always want a positive delta G. We want there to be excess energy left over to do work, to do stuff, right? So our E for a cell, we also want that to be positive because we want electricity to flow. So anytime you have a positive G and a positive E, we can definitely say without any reservation that the overall reaction is spontaneous and we've got the ability to do work, which is good. So delta G has a relationship with E in this following formula right here. So this is another really important formula that I would strongly recommend you try to memorize. And it goes something like this. Delta G is equal to negative, oh my gosh, it's so hard for people to remember that negative NFE. Okay, and just a little bit of clarification. N is equal to the number of electrons that are transferred in the balanced reaction. So the key thing is that it has to be balanced. So for us, when we were working with zinc and copper, you had one reaction releasing 2 electrons and the other reaction was absorbing 2 electrons, and that was perfect for us, right? But they're not always going to be the exact same number of electrons, and you may have to adjust these little reactions in order for the number of electrons to be balanced. And I'll show you guys how to do that. So in our balanced reaction, the number of electrons being transferred was 2. So we would have filled in a number 2 here. And then the Faraday, the F is called a Faraday. And what a Faraday is it's 96,485 coulombs per mole. This value is sometimes called the charge of 1 mole of electrons. And we can also rewrite it as like a coulomb. What it is that a coulomb is joules per volt times, that's what a coulomb is joules over volts. And then since a Faraday is coulombs per mole, we just say joules per volt mole. Sounds a little crazy, but we'll talk a little bit more about how a Faraday is a very important value because what Faraday did, it was named after a gentleman by the name of Faraday. And what Faraday was able to do is take a look at balanced reactions and determine, remember how like one electrode was gaining mass and one of them was losing mass? He actually did a bunch of math to determine exactly how much, or figured out that there's a relationship between exactly how much one of the electrode loses mass and how the other one gains mass, and directly correlated that with how many electrons are passing through that voltmeter. So every time an electron passed through the voltmeter, you would basically be able to see that and measure it by determining the amount of mass that was lost or gained from either electrode. Super clever. So there's a direct relationship between voltage and this thing called a Faraday, and basically it's the charge of 1 mole of electrons. It's pretty cool. It's measurable. So you have balanced reactions through stoichiometry, and stoichiometry can therefore be used with Faraday, electricity. That's basically what I'm trying to get at. All right, so anyway, in your book, it does also start talking about something called a Nernst equation. And I want to make sure you guys know that in the current AP guidelines for AP chemistry, the Nernst equation, calculations using the Nernst equation, is not necessary. So thank goodness we don't have to worry about that. But they do want you guys to be able to use your intellect about Le Chatelier's principle to be able to figure out what certain things could cause a change in the overall reaction. Because the thing you have to understand is that we have the perfect setup for an equilibrium going on here. So the flow of electrons can be adjusted or pushed or changed when you make certain changes to the overall system. So let's think about some of the things that could cause a change in the flow of electrons. One thing that can cause a change in flow, and this relates back to kinetics, is what do you think will happen to the rate of the reaction if I were to heat up the entire system, everything, if I were to heat this whole thing up? It would cause the reaction to go at a faster rate. And that faster rate would actually cause those electrons to flow a little faster. And if they're flowing a little faster, this little voltmeter is going to be able to pick up that change because the electrons are going to flow through the voltmeter at a faster pace. So we can actually change the rate at which the reaction occurs by increasing the temperature. Here's another really good question. What do you think would happen if I increased, or no, let's do the opposite. What do you think would happen if I lowered the concentration of both of these solutions so there's not nearly as many ions in solution? Don't you think that's going to have a direct effect on the amount of zinc or copper ions produced or absorbed? Well, yes, and if we adjust that, then this little voltmeter, oh no, he's not going to be able to be quite as active because there's not going to be quite the same amount of flow. So if you reduce any of the concentrations of the ions, you're going to reduce the voltage and slow down the reaction. All right, so Le Chatelier's principle is more important than doing actual calculations on the change in concentration or the change in temperature. Okay, the last thing that I'm going to show you guys how to do is something called cell notation. Cell notation is just a shorthand notation to show you guys exactly what's going on in your voltaic cell. But there are a couple rules. Over on the left side, you have to have the oxidation going on at the anode. And on the right side, you have to have something going on with the reduction cathode. So anode on the left, cathode on the right, starting with oxidation, ending with reduction. So in our previous example with copper and zinc, you have to think which one was being oxidized, which one was, oil, oxidation is lost, which one was losing electrons or basically producing the electrons. And that was your zinc. So what you started with, and you always start with what you actually had at the very beginning, what you started with solid zinc. All right, and that's what we started our zinc off with. And then that zinc turned into a zinc ion, correct? So what we do is we just kind of separate and draw a line straight down just to kind of symbolize that, hey, this is what zinc is turning into. Zinc is turning into zinc the ion in solution, right? He's aqueous. And then on the other side of the reaction, on the other part of this electrochemical cell, we had the copper being able to receive those ions, right? So what we like to do is to separate the left from the right by a double line, something like that. And what we started with is the copper started off as an ion in solution, correct? And those ions in solution are what basically pulled or attracted the electrons that were being produced by the zinc. And once those copper ions grabbed onto those electrons, the copper would literally turn into copper the metal. And so we're just showing on each side the process that is occurring one step at a time. All right, now what I'm going to do is I'm going to take a pause just to talk a little bit about what's the best way to set up the cathode and the anode when you have like two, maybe half reactions that you're looking at. So the most critical thing that you want to check is you want to go back to the reduction half cell potentials to figure out which one would actually prefer to do the reduction potential. So whichever one of these processes has a more likelihood to be reduced, that's the one that you want to make be the reducer. So you guys remember the red cat? So whichever one is the most likely to be reduced or the more powerful, has a more powerful attraction for the electrons, you want that part to be your cathode. All right, so this requires you to look up some of the cell potentials. So I've actually got that sitting right next to me. And if you're curious, this is actually on page 857 of your textbook. So let's go ahead and look up some of these values and just see what we've got going on here. So this guy right here, the CR207, this guy has a reduction cell potential of 1.33, and that's positive, 1.33 volts. Now let's check on this iodine dude. This iodine guy has a cell potential of positive 0.54. So 0.54 volts. So obviously we're going to make this guy be our cathode. All right, so we're going to have this guy be our cathode. That's where reduction happens. And we're going to make this guy be our anode. Okay, so we're going to actually want to take this reaction right here and flip it. So that's what I'll do. I'll make it 2I negative. So it'll start off as iodine in solution. And then it's going to turn into solid iodine. And in that process, it'll produce our 2 electrons. Now, looking at the reaction, the first reaction here with the CR207 ion, I want you to notice how many electrons it requires. Do you guys see how it needs to absorb 6 electrons? But you see how this iodine is only being able to pump out 2 electrons at a time. Well, we want these 2 electrons, the electron quantities, to be exactly the same amount. So what I'm going to do is I'm going to have to balance this, this whole thing out. So what I'm going to do is I'm going to grab this guy right here. And instead of only producing 2 electrons, I want it to be able to produce 6 electrons. So I'll be multiplying this bad boy by 3. And this is kind of like Hess's law. You just need to combine all the stuff that's on the left side of the arrow. And since the electrons are going to be the same on both sides, you see how if I multiply this guy by 3, I'll have 6 electrons being produced. And then you guys see how 6 electrons are going to be absorbed. So you're going to see the electrons disappear, but everything else is going to remain. So on the reactant side, we should have the CR207 remaining. So CR207, this is the ion. All right, we're also going to have a bit of hydrogen ion, so this must be some kind of acid that's going to be present. Okay. And then I'm going to make sure that I multiply the 3 over here with this guy, with the ions there. So I'm going to have 6 iodide ions in solution. All right, let's see what we got on the product side. Okay, on the product side, looking at that first one, it looks like I'm going to have 2 of the Cr3 plus ions. Looks like I'm still going to have some water, 7 waters. And then now look at the product side of this other guy. Looks like I'm going to have 3 iodide solid. Okay. So here is the grand total reaction for the entire process. And here's a really good question for you. When you have to multiply the reaction, you see this iodine reaction, how I had to multiply it by 3 to make the number of electrons balance out. Do you think that's going to have any effect on the voltage when I have to multiply that reaction out? Well, the correct answer here is no. You see, this cell voltage, it's kind of like the maximum voltage that you can get, and it can only pump out so much. That reaction can only pump out so much. So it's basically kind of thinking of it kind of like this. This iodine right here, every time it reacts in this ratio right here, it's going to pump out 2 electrons. And so we'll pump out 2 more electrons, and then we're going to pump out 2 more electrons, and then finally you've got 6, and so therefore this guy can finally react. So it doesn't really change the voltage at all. It just takes a while for the electrons to build up in order for that chromate to finally react. So every time So every time 2 of these react, so you go down by 2 iodides, every time 2 of those ions react, you're going to produce 2 electrons. And when you finally get up to 6 electrons, that's when this guy can finally react. All right, now that you finally have everything figured out, remember, we always look for some kind of positive value, but because you had to flip the anode value, this 0.54, because we had to flip the reaction, that value is actually now going to become negative. So this is going to become a negative 0.54 volts. Okay, and the other guy is still going to be positive, luckily, so that's going to be a positive 1.33 volts, and so let's combine it. And I get an overall charge of, or voltage of 0.79 volts. So it's still positive, right, and it's still going to work. And so basically the reason why I'm showing you this is just because sometimes you're going to have some really peculiar little half-cell reactions, and you still have to be able to combine it. You still have to be able to show the overall balanced reaction. And if I were to do like a notation on this one, like like we showed over here, like a cell notation, but when we do cell notation, the coefficients don't matter. So my strongest recommendation for you guys would be to go back to your standard cell potential listing and look at the reactions that they actually provided you there. So remember, over on the left, we want the anode, where the oxidation happened. So we would start with our iodine. The iodine started off, remember we had to flip the reaction. This is the original reaction, but we had to flip it. So I'd actually start with the 2I negative AQ, because that's how it started. Draw a line, and that was going to change into I2 solid. Okay, and then we're going to split that sucker and come all the way up to the top. We're going to be looking at the starting material. Never show electrons. So this will be Cr2O7 2 minus plus 14H plus. Okay, because that's what we have over on the left. Draw a line. And then on the right side, we're going to show the 2Cr3 plus AQ plus the 7H2O. Whew. All right, so even though we changed that second half reaction and we had to multiply it by 3, when we show the cell notation, we don't show the multiply by 3. We just show the core cell reaction that's going on. All right, everyone, and just one more final note about something that I thought was an interesting discussion on some of the AP Chemistry boards that I follow regarding whether or not you guys have to learn how to balance oxidation reduction reactions as seen maybe like on page 846 to 847 of your textbook. Your textbook goes through a very long, detailed explanation about how to balance reduction and oxidation reactions in an acidic solution. And then later on they tell you how to do it furthermore in a basic solution. Well, I've got really good news for you. It does not appear that you guys are going to be needing any of that skill. But I do want to caution you on what they do expect you to do. So as long as you remember that the half reactions are going to be given to you, and that all you have to do is balance the charges, and then just make sure that your atoms are balanced, I think you guys are going to be just fine. So taking two of the half reactions, they should be provided to you just like in this sample problem here. You should be able to therefore balance the charges, therefore balancing the atoms on both sides, and then getting your full electrical potential, the voltage. All right, you guys, that's all for now, and good luck.